looking through what was required to enable our standards for safety and charging speed, we started to see some desires in cybersecurity, our ability to pull data off the aircraft, and where we were doing the computation for optimal charging that necessitated a better data and communication pipeline than existing charging standards such as CCS could enable. CCS has the option to use power line communication to transfer data from the vehicle to the charging station, but it's limited to about 1 megabit per second. And our math indicated that we wanted to go far beyond that, multiple orders of magnitude more data bandwidth. So what developing an all-new standard unlocks with GEACS is that we could add a new means of transferring data between the vehicle and the charging station. We added a 2.5 gigabit per second T1 Ethernet connection in the charge handle connection, in the charge interface, that allows the aircraft to stream data down to the charging station in a secure fashion. The data stream is limited in hardware to be one way, so there's no cybersecurity risk in that interface.
Nice. Okay.
But the aircraft can stream vast quantities of data about its current state through the charging process, as well as just general purpose data. Let's say if we want to transfer data from the previous flights, records of the previous flights, down to the charging equipment, we can do that. And that enables us to one, have a faster charging sequence, and I'll talk about it in a second, but we can have data available on the ground support equipment that's been securely pulled off the aircraft that can be used to analyze the current state of the aircraft for predictive maintenance, for example. So we can see is some component on board the aircraft trending in a bad direction. We can then preemptively or proactively schedule maintenance work that we otherwise wouldn't have been able to know that we needed to do.
Got it.
On the charging side, with existing charging standards, the decisions around the charging process are primarily made on the vehicle side. So the vehicle looks at all of its all of the sensor data that's coming in from its batteries, its records of what the batteries have been up to over the period previous to the charge, and it decides this is the voltage and current that I want to be charged at, and it sends a current limit to the charging station. And then the charging station basically just tries to do its best to get up to that current request. We wanted to go beyond that. When you're running an air taxi operation, you have the opportunity to forecast what is the next mission this aircraft is going to be doing. What is the current state of the power infrastructure at the building where the vertiport is situated? What is the current state, in our case, of the cooling system?
Right.
And knowing all that information allows you to maybe make a different decision than you would if you only had the information that the vehicle has on hand. So by streaming a large amount of data from the aircraft, in this case like raw battery temperature data, individual cell voltages, pressures of various points in the fluid system, we're able to have a higher, more complex level of charging optimization by transferring all that to the aircraft, running computations on board the ground support equipment with more computational power to make a decision for the optimal charging profile.
So there's another weight savings there. We can now have more computation because it's part of the charging system, or is there more to it?
Yeah, so it could potentially be a weight savings. You could have more complex computing hardware on the ground. It's also a benefit from a continuous development perspective. So anything on board the aircraft, in the sake of safety, we want to have anything that goes on board the aircraft, any change to the software or hardware on board the aircraft has to go through a very, very rigorous review and testing process. But for charging, we might want to continuously update the optimal charging sequence for a given aircraft. Maybe every week we want to be continuously pushing small little tweaks and updates to optimize that process, which if we were to put those algorithm optimizations onto the aircraft side, we would be very delayed in our development process.
Right.
But by having it on the ground support equipment, we are freed to be continuously updating at a much faster way. We still go through a rigorous review process, but it's not quite to the same levels as is necessary for an aircraft that you're trusting with
Nice.
your life.
So when I think about Tesla doing over-the-air updates, maybe you can do that with the S4, but to your point, it would still have to go through like a full certification round. And so now, by being able to make this software changes to the ground support equipment instead, yeah, it allows a fast. Wow. So you're really speaking my language on the continuous delivery side. That's a very software thing to do.